cylindrical and spherical coordinates. Actually, I'm talking about cylindrical coordinates and spherical coordinates. All right, so what's a cylindrical coordinate? First, cylindrical coordinate system. Well, cylindrical coordinate system is a way to represent the position of a point in space by using r theta and z. Here, r theta means the r theta you use for polar. We know already that using the polar coordinate system, we can represent the position of any point in the two-dimensional space, right? And then from any position in the two-dimensional space, if you go up or down by using the z value, you can represent the position of any point in the three-dimensional space. Does that make sense? Right? Okay. So this is something that you would already know, because all it is just throwing an extra coordinate, z coordinate, into the polar coordinate system that we already know. Okay? So there's not much to say. However, spherical coordinate is something totally new, so I need to explain this further. So what is a spherical coordinate system? This is a coordinate system which uses rho and theta and phi. And this rho, although I spoke about rho representing density usually, this has nothing to do with density. It's, sadly, we traditionally use the same symbol rho for this quantity here.
So is that P?
Huh?
Is that P?
No, that's not P. That's rho. Oh, that's not P. Okay. All right, can I borrow your notebook? All right, thank you. All right. Okay, so let me try to explain what a spherical coordinate system is. Okay. So suppose you have a point in space, okay? And let's say this is x, that's y, and that's z. What you do is you start with your notebook on with this side on the z-axis, and this entire thing on the yz plane, and then xz plane, and then you start opening this notebook until this page here entirely contains that point. So the plane given by this page here contains that point. Okay? So you open this until it reaches that point. And the angle that you open this is what you call theta. Does that make sense? That's the angle theta, right? And then from that point to the origin, the distance between the origin to that point is called rho. Rho is the distance from the origin to the point. Okay, and then then phi. These are, by the way, all Greek symbols, right? This is R, TH, and F. Okay, those are the way these are sounded. Okay, and this is called phi. This phi, going back. Okay, so open, you get the theta, distance, you get the rho. Finally, the phi is the angle from the North Pole. So if you had something from the North Pole and you went down and you met with this point, this angle from the North Pole to here is called phi. That's what phi is, right? Okay, so here's my best attempt at drawing what I just explained. All right, so you have this point in 3D. Okay, here's a point in 3D, and you start out by figuring out a page that contains this point, and this angle is theta, this distance is rho, and this angle here is phi. Okay, that's my best attempt at explaining this coordinate system. Okay. All right, that's called spherical coordinate system. Maybe a good way to understand this coordinate system is by thinking of an explicit point in space and trying to represent it in terms of cylindrical and spherical. So let's try that. So, question: convert 1, 1, 1 rectangular into cylindrical and spherical coordinates. All right, so let's start with cylindrical. Now, there's one thing I should have said before solving this. That if you go from x, y, z to r, theta, z, the z coordinates are the same. So we know already what this should be. It should be 1 because that's 1. Okay. And usually you want to go from the rectangular to cylindrical first and then go to the spherical, because if you think about what this theta is, that theta is this angle right here. So it's same as this one. Okay? So again, I'm trying to say that cylindrical coordinates and spherical coordinate share the common theta. This theta will be same as that theta. So once you convert this into cylindrical, then you can reuse this to be over here. So the correct order of getting the answer is to find this first, and then we'll try to get that. Okay. All right. So now let's try to get this one. So z is 1, and all we need to do is to now take this x comma y, which is 1 comma 1, and then think about r and theta here. Okay. So what's the distance from the origin to here?
Red 2.
Red 2, because we use the Pythagorean theorem, right? 1 squared plus 1 squared is r squared. If I solve that, r is equal to square root of 2. What's this angle?
45.
45 degrees. In radians, what's that? Pi over 4. Okay, so in cylindrical coordinates, it's radical 2, comma pi over 4, comma 1. Okay. I wrote down CYL so that it represents the cylindrical. But usually you can figure it out by context. So a lot of times it's not written at all. But if you have various coordinate systems used together, you want to distinguish them by using these abbreviations. Yes. Okay. All right. Now we go to here. Now there's a difference between r and rho. R is the distance from the origin to the foot of that point. So see, this r theta represents the position in 2D. So if you have something in 3D, you have to bring it down and think about the foot of that point. Okay? So r is really this distance here. Okay? And rho is this distance. Okay? So I guess for rho, it's easier to just think about the distance from 0, 0, 0 until 1, 1, 1. What's the distance from 1, 1, 1 to 0, 0, 0? So rho is square root, just use the distance formula, right? 1 minus 0 squared, 1 minus 0 squared, plus 1 minus 0 squared. That's the distance from 0, 0, 0 to 1, 1, 1, which is 3. And we have theta, the same thing, so theta is pi over 4. That doesn't change. And therefore, the only thing that we have to worry about now is the angle phi. Now that actually turns out to be harder than you would imagine, because think about the picture again. So let's draw the picture. Okay, so we're talking about distance 1, 1, 1, and this point here is really 1, 1, 1, right? And we're trying to find the angle from Z, the North Pole, to this point, right? And therefore, we're looking at the angle from here to there. And a good way to picture it is by taking this slice. You take this cube that contains 1, 1, 1 as one of the vertex. You take this slice diagonally, so you get 2 prisms. And if you look at this cross section, this is what you get. You get a rectangle whose height is 1, and whose base length is square root of 2, because it's this length here. It's 1, 1, and therefore it's square root of 2. So it's wider in the base than the height. Okay. And what angle are we looking at? We're looking at the angle from the North Pole to this point. This is 1, 1, 1, 1. and that's the z-axis. So you see how I'm taking the slice of? So I take this slice, and if I take this over here and put the point over here, this is the slice that I get, okay? And the angle phi is what? I'm looking at this angle phi. Since this length is square root of 2 and this length is 1, I can use tangent. And say tangent of phi from SOHCAHTOA, tangent is opposite over adjacent, so root 2 over 1. And this over that. So that means phi is tangent inverse of root 2. And that happens to be none of the usual special angles that we know of. So if you don't have a calculator, we'll be stuck with this. Okay, you can't do anything else but to say that as tan inverse of radical 2. So for the spherical one, the answer is square root of 3, comma pi over 4, comma tan inverse of square root of 2. I mean, I know that this is less than square root of 3, tan inverse of square root of 3, which is 60 degrees. And it's more than 1, so tan inverse of 1 is 45 degrees. So it's an angle that's between 45 to 60. Does anyone have a calculator? Should be 50-something degrees. Because it's less than 60, but over 45.
54.7.
Okay, yeah, so it's 54.7 something, but it's not one of the special angles, so you have to leave it like this if you don't have the calculator. Okay. So that's the answer in terms of spherical. All right, now I want to conclude this section by coming up with formulas for these. So what's the formula? First, for cylindrical and rectangular, we already know what it is because I already have the formula for the polar, right? So what are the formulas that you remember from polar to rectangular? It's r is square root of x squared plus y squared, right? And then theta is tan inverse of y over x plus alpha. You may have to add 180 degrees or subtract 180 degrees depending on your quadrant, right? And x and y are obtained from r and theta by r cosine theta and r sine theta. Okay. All right, and then we have to know how to go from cylindrical to spherical. And here's the picture that you want to draw. See, if you have this point, so if you have a point, this angle is phi, and this distance here is r, this distance is rho, and this height, if you project it to the z-axis, this is z, right? And then, so it's really, this is really 90 degrees. It's a three-dimensional picture. So there's one triangle that you should know how to draw rather than trying to memorize the formula, because if you know this one triangle, you know everything, okay? So it's like this. If you take this right triangle and just put it like that, this angle is the angle from the North Pole, so that's phi. Right? And this is really the z-axis, so this is the height, so that's z. And this is the distance from the point to that point, to the origin to that point, so that's rho. And this distance here is same as this distance, so that's r. So you can think of the r as the distance from the point to the z-axis. Okay. So that's the picture, and it's a right triangle. Okay. This right triangle is drawn here as a three-dimensional picture. Okay. Now this tells everything because you can use SOHCAHTOA to say, first, what's rho? Rho is by Pythagorean theorem, z squared plus r squared, square root, right? It's the square root of r squared plus z squared. And then if you use this one, that r squared is x squared plus y squared, you have x squared plus y squared plus z squared. Okay? So you have these two formulas for r, rho. If you have r and z in cylindrical coordinates, you can find rho by using this. Or if you have the point in rectangular coordinates, you can use this formula to get rho. Okay? So it's very handy. Now, how would you get phi? Well, phi is tangent inverse of what?
R over Z.
R over z. It's opposite of radiation. So it will be tangent inverse of r over z. Now, the only problem with this formula is sometimes your angle could be more than 90 degrees. If you have anything in the southern hemisphere, the phi has to be beyond 90 degrees, right? And in that case, tangent inverse cannot produce the correct angle because tangent inverse only produces angle from negative 90 to positive 90 degrees, okay? So that's always a problem. So things that people do is sometimes people just use cosine inverse. So cosine inverse will be cosine inverse of z over rho. If you do that, then it always produces the correct one because cosine inverse produces angles from 0 to 180, okay? Or you can say, you might say, put a warning here and say plus 180 degrees if z is negative. Okay, so that way you can find out what phi is. Now, how do you go the opposite? How do you get, so these formulas tell you how to get rho and phi if you're given r and z. R and z belongs to cylindrical. So if you have cylindrical coordinates, you get the spherical by using these formulas. Theta is same as theta, so there's nothing there. Okay? So now you have to know how to go back. If you're given rho and phi, how would you get r and z? Well, here's the formula. You get r by doing rho times what? Sine phi or cosine phi? Sine phi, because it's the opposite, right? And then you get z by rho times cosine phi. And then furthermore, because x is r cosine theta, this thing can be transformed into x and y, and you, by replacing r by rho sine phi, you can say x is rho sine phi cosine theta, and y is rho sine phi sine theta. Okay? And that's all. These are the formulas you need to know in order to do any calculations converting cylindrical, spherical, and rectangular in any way.
So you have to memorize all these?
You have to memorize all this, but as I said, it's better to remember this single picture.
Right.
So I'm assuming that you already remember this because we have had many exposure to this. And rather than trying to memorize all this, just remember this single picture. And if you know that, then it's easy to figure out all these formulas.